Today, we will take a look into exponential growth and decay. Now, the main idea here is that when it comes to exponential growth and decay, most of the time it's always going to be in relation to time. And this is the main idea of what an exponential growth and exponential decay is. So, as time increases, as you're moving on in time, a function can increase or decrease at a greater rate. And that is what we call an exponential growth or decay. If we were to graph those situations, this is what we would obtain for exponential growth, and this is what we would obtain for exponential decay. Now let's see what this means. For an exponential growth, notice that at the beginning, if we look at this interval right here, when x is our time and y is just an example, it's population size, notice that at this interval, you don't increase that much. But notice that if we were to get the same interval here, or at least the same, approximately the same, when it comes to the time, notice that you're increasing faster. Now, what would if I would look at, they're about the same size of an interval. Now, in the third interval, it's increasing even faster than the second or the first interval. Now, if we were to look at another interval, notice that this is increasing even faster than the previous intervals, and so on. So look that as you're moving on in time, you're just increasing faster and faster and faster, and that's what gives it this curve shape. And for exponential decay, what's exactly the opposite? Let's look at what happens between 0 and 1. Well, you're decreasing real fast. You went from 0 to 1, you went from 0 all the way to 5. Now what happens between 1 and 2? Well, you went from 5 to 2.5. So notice that as you're moving on the x, you're decreasing in a slower rate. So this is just a visual interpretation of what an exponential growth and an exponential decay is. But now let's actually look as to how it actually can be explained using algebra. So we already saw this. An exponential growth looks like this, exponential growth, and exponential decay looks like this. So now, is there a way for us to identify if we have an exponential growth or an exponential decay just by looking at an equation? Well, yes, there is. And this is how an exponential growth looks like. This is a function for exponential growth where notice that there are three variables in this function. Where a, we're going to call that the initial amount. R, we're going to call that either the growth or decay rate. And T is going to be the time. So notice that all you need to know are the values for those three variables. And if you know those values for three variables, then you can actually write down an equation for either an exponential growth or an exponential decay. Notice that there's a slight difference between exponential growth and exponential decay, and that is when it comes to exponential growth, you're adding the rate, and we will talk about what a rate is in a second. But when it comes to decay, we're not adding the rate, but we're subtracting the rate. So those are the two differences when it comes to algebraic equations between exponential growth and exponential decay, where A is the initial amount, R is the rate, and T is the time. Let's actually see how we can interpret a real world example when it comes to exponential growth and exponential decay. And for that, we're going to look at example A. The direction says, identify if following it's an exponential growth or an exponential decay. And use the given formulas to answer the question. Well, let's read the scenario here. Well, it says a new car that sells for 18,000. I'm just going to highlight this because it's important. Now, it says here that it depreciates. It depreciates at a 25% each year. Now it's asking us to write a function that models the value of the car and find the value of the car after 4 years. So the first thing that we want to do is this exponential growth or exponential decay? And notice that, at least in this example, the word depreciates gives you the clue to see if it's an exponential growth or an exponential decay. If something depreciates on value, then that means that the value of that product is decaying. It's actually going down on price. Because it depreciates, then we know that we have an exponential decay. So let's stop for a second here and let's look at our formulas. We know that it's a decay because of the word depreciates. And because the decay, we know that our formula will look like this. Y equals A parenthesis 1 minus R exponential t. That comes from the how we started this lesson. So now let's see. Can we use the given formulas to answer the question? Where the question is, let's find the value of the car after 4 years. Can we do that? Well, in order for us to figure that out, we need to know what A, what R, and what T is. Remember that A is the initial amount. Where if we read this example, it says a new car that sells for 18,000. So here A has a value of 18,000. Now the value for R is the rate. And the rate most likely will always be given to you in percentage. So if we look at example A, it says it depreciates at 25%. So the rate is 25%. But here's the deal. If we want to use this formula, we don't want the percentage. We want the decimal representation for our percentage. So for that, we need to transform this 25% into a decimal representation. And to do that, we got to use our calculator. So we're going to get the percentage, which is 25, and to convert it into a decimal representation, we're going to divide it by 100 because there's 100% in a whole unit. So that means that the rate is 0.025. Now, what time are we interested on? Because we just need the value for t, but it says here that we want to look into 4 years. So here t is 4. Once you know the value for those 3 variables, then you're good to go. We can actually find out the value after 4 years because we do have a formula that can give us that. So that becomes y equals a, which we know is 18,000, parenthesis 1, oops. So it's 1 minus r, where r, we don't use 25%, we use 0.025. So 0.025, and the exponent t, which is 4. Perfect. Let's find out what this is using our calculator. So we're going to do 18,000. I think I put an extra 0 there. So 18 and 3 zeros. 1, 2, 3. Open parenthesis. 1 minus 0.025. Close parenthesis. And this 4 is an exponent. So we use this button to do exponents in the calculator. So exponent 4. So there it is. It says that y equals 16,266.38. But now what this means, this is just a number, but we got to put an actual meaning to it. So that means that you bought a car at $18,000, and because it depreciates 25% each year, then that means that after 4 years, what your car is worth is $16,266.38. And that's what it means by depreciation. To depreciate is to say that the value of the unit it's losing some value, which is exactly what it says here. You start with 18,000, after 4 years, its only value is 16,266. Let's look into another example here. So the first thing that we want to do is, well, is there exponential growth or exponential decay? Well, let's see. It says the bird population increases at a rate of 2% per year. There are 1,573 bears this year. And we want to write a function that models the bear population after 10 years. Okay, so It's telling us right here explicitly that this is an exponential growth, because if the population is increasing, then that means that the population is growing. And we know that the formula for exponential growth looks like this: 1 plus r exponent t. So now your job is to figure out the value for a, r, and t. Where a is the initial amount, so if we read the problem, we say that there are 1,570 bears this year. So that means that you start with this how many bears. Now the rate, it's telling you right here, the rate is 2%. But remember, we don't use 2%. We got to transform that 2% into decimals. So now that becomes 2 divided by 100. So that becomes 0.0502. And the time, we're looking at 10 years. Perfect. What we have to do is just plug it into the formula now. So that means that y equals 1,573, 1 plus r, where r we're going to use the 0.02, and an exponential 10. You have an expression. Let's find the value of that using the calculator. So 1,573, parenthesis 1 plus 0.02, open parenthesis, exponent 10. So that means that we got y equals 19, 17, 47. Let's just keep it at, well, let's round it to 48. Perfect. So that means that you start with 1,573. And now, after 10 years, you have 1,917. Well, you don't have a 0.48 bear, so let's just keep it as 1917 bears. So now, here's your entrance ticket. First, identify if it's an exponential growth and decay, and then use the given formulas to solve the following problem.